Okay, it's recording now. And here's PowerPoint. Okay. So welcome to the 12th recitation. And let's get started. So today, where did my mouse go? Okay. Today we're going to be learning about cache metrics and cache-friendly code. And yeah, so let's start off with cache metrics. And so we've been talking a lot about caches. So we should also talk about different ways to measure like how well a cache is performing. Um, so one way to do that is to calculate the miss rate. And the miss rate is the fraction of references that aren't found in the cache. So basically out of all the times that you try to go and look for something in the cache, it's the percentage of time that you don't find what you're looking for. And that's equal to 1 minus the hit rate. And yeah, so and then there's also the hit time, which is the time it takes to deliver to go into the cache, find a set, and deliver a line to the deliver a line back to the processor from the cache. And that includes the time to determine whether the line's in the cache. So also finding the tag bit basically by traversing that set. And these are just typical numbers here as examples: 4 clock cycles for L1, 10 for L2. And then we also have the miss penalty, which is the additional time required because of a miss. So when we miss, we have to go. So first we go and check in the cache to see if something's there. If it's not, we have a miss. And when we have a miss, we then have to go and go into main memory and fetch what we want. And that adds time. So that's what the miss penalty refers to. And then we also have the average memory access time. So when we have requests to the cache, it could be either a hit or a miss. And so it's basically the average time over all of these requests. And we have a formula here for that, which is H, which is the hit latency, which we just talked about here, and the miss rate multiplied by the average miss penalty. So let's take a look at how this formula works. So if we're given these parameters, so the hit latency of the L1 cache is 1 cycle, and the hit rate of L1 is 30%, and the latency is 200 cycles. So we just plug it into the formula. The H is 1 cycle. And then to calculate the miss rate, we need to do 1 minus the hit rate, which would be 70%, 0.7. And we multiply that by the number, by the average miss penalty. So basically, when we miss, it takes around 200 cycles for it to access the data from the main memory instead of the cache. And when we multiply all this together, we get 141 cycles. And so, okay, yeah, 141 cycles for the average memory access time. And then we also have multi-level caches, right? There isn't just an L1 cache, there can also be an L2, L3. So basically, the average memory access time for an L1 cache, we have the hit rate for L1, or sorry, the hit latency for L1. And then we have the miss rate for L1. And then we have to multiply that by the average miss penalty, right? But the average miss penalty in this case isn't going straight to main memory. It's going to L2 and then L2 going to main memory if it's not there. So yeah, in this case, we have the AMAT of L2, and then the AMAT of L2 we know how to calculate because that talks directly to main memory. So it's basically all these same parameters, but replaced with L2. And we have the average miss penalty here for accessing main memory. So if we're given these values, we can calculate what the average memory access time is for the L1 cache in this case, and it'll basically be this formula, because what we do is first we calculate it for L2, which is 10 plus 1 minus 0.55, which is 0.45 times the 200, and then we do and then the H value for L1 is 1 cycle, and the hit rate is 30%. So that translates to a miss rate of 70%. And then we plug in whatever we got for the L2 cache into L1, or into the AMAP for L2 here. And once we do that, we basically get this final result, which ends up being 71 cycles for the average memory access time. And yeah, so something interesting is that a 99% hit rate is considered twice as good as a 97% hit rate, which sounds pretty strange intuitively initially, but when you think about it more, it makes sense. Yeah, so okay, yeah. So to calculate the average access time for 97% hits, we have the 1 cycle. And because we define that the cache's hit time is 1 cycle and the miss penalty is 100 cycles. So one cycle is the H value. And then our miss rate is 0.03, because it's 1 minus 0.97. And then our third value is 100 cycles, which puts us at an average access time of 4 cycles. But for the 99% one, the 0.03 and the 0.01 make a big difference. So when we replace that with 0.01, it ends up being 2 cycles for the average access time. So it actually takes cuts it down by a factor of 2 when we have 99% hit rate. And yeah, so now we could talk about cache friendly code. And so basically the part of your code that'll take the longest is like the core most important functions and the inner loops inside those functions. And yeah, so we could minimize the misses inside those inner loops by exploiting temporal locality, where we get access to the same variables, such as the variables that are used to actually make that loop run. And maybe you're adding to a sum or something like that. And there's also, we could also exploit spatial locality, which basically gets, like if you're accessing an array and you're accessing index 0, index 1, index 2, that's what the stride 1 refers to. And so let's talk about this code, and let's consider what the hit rate of this code would be. So we have, so let's assume that in our cache, in each line, there's a 64 byte block. And we know that an int is 4 bytes. So, and so this is our code. We have an array, m rows, n columns, and we just iterate over it. And we're just adding 1 to each value in that array. And so if we think about how that array is stored in memory, it's stored as a like one dimensionally, not actually as a two-dimensional. No, it's not actually like two-dimensional in memory. So we have our row 0, row 1, row 2, all the way up to row m minus 1. And So if we think about this inner loop here, it's kind of um, going left to right, right? It's going through the rows, and so when it goes through the rows like this, that's good for us because um, because for example, if we access array A at some row and some column, it doesn't only load that single int into the cache, right? It loads a whole block. Hold up, let me just mute everyone. I think there's okay. Yeah. So yes. So this is helpful for us, or this piece of code is is kind of cache friendly because when you load something, it loads the entire block. So an entire row might be loaded. And so when we actually do this, when the inner loop runs and goes through all of the columns in the row, that entire row might be loaded into the cache, and that makes the computation a lot faster. So if we think about it now, yeah, so we have the same code, 64-byte block, 4-byte integers, and if we want to, yeah, so basically when we access A at row 0, it's possible. So let's say a block. So if a block is loaded when we access that row, we could determine how many integers that block will store, because we have a 64-byte block and each integer is 4 bytes. So if we divide them, we find out that we can store 16 integers inside of a block. So when we access something, okay, so when we initially go to access when we initially go to access A at row 0, column 0, it's going to be a miss because it's a cold miss. But then um, when we do that, we'll go and load this block of 16 integers into the cache, right? And when we do that, the rest of the things that we try to access will be hits, and because we loaded all the 16 integers. So the first one's going to be a miss, and then it'll be followed by 15 hits, right? And then the next one's going to be a miss because that's all the 16 integers we stored. And then after that, the rest of the 15 are going to be hits. So in this piece of code, the hit rate is 15 out of 16, and that's pretty good. So yeah, that's how we could think about the hit rate of this code. But to do that, you need to know the configuration of your cache. Okay, so now we could talk about matrix multiplication. And yeah, so let's say we're multiplying n by n matrices, and let's say the matrix elements are doubles, so they take up 8 bytes, in contrast with the ints that take up 4 bytes. And this triple for loop is going to result in an O of n cubed runtime, and there will be n reads for each source element. And yeah, so basically this is kind of the description of the example that we're going to be going over. And so let's try to think of, let's analyze the miss rate for this matrix multiply code that we have. And let's say this is the configuration we have. So we have a 32-byte block size. So if it's 32 bytes in a block, 8 bytes per double, 32 divided by 4 by 8, that gives us 4 doubles. And let's say the matrix dimension is very large. So so the cache actually doesn't hold a lot of the matrix when you access something, right? And if that's the case, then our our miss rate will actually be pretty high, right? Because we won't be able to store a lot of the matrix inside our cache. And yeah, so let's just kind of go over this example and think about it. So we know that C allocates arrays in row major order, and so they're stored contiguously in memory. And yeah, so we could just move on to the example. Yeah. Okay. So let's analyze this initial code where we have an IJK, an IJK loop, right? So in this case, we're going through um, for um, matrix A, we're traversing it row wise, right? And for matrix B, we're traversing it column wise. And when we access C, it's a fixed value. It's just we're just accessing C at IJ. But for A, we load a row. So this inner loop is doing the most work here. So the outer loop just loads is just it's going to be static until k equals n. And as for B, the j or yeah, so here the j will be static until k equals n. So here we're going through the columns. Here we're going through the rows, right? Or I guess here we're going through the columns, and here we're going through the rows. But we're really going through A row wise, because if we're going through each of the columns in A, that means we're traversing it row wise. And for B, we're going through each of the rows. So when we go through each of the rows, we're actually traversing it column wise, because we have this whole column highlighted that we're going through. And so if we think about this, in this case, let's think about the misses per inner loop iteration for our arrays A, B, and C. So in this case, let's talk about A. And since we're going through it row wise, and we know that we can store 4 doubles at a time, right? This array stores doubles. When I equals a certain number, it'll load it into the cache, right? And so the first one's going to be a miss again because of the cold miss. And then the rest of the next 3 are going to be hits. And then the next one's going to be a miss. And then the other 3 are going to be hits. And so for A, the miss rate is actually 0.25 because we miss 1 out of 4 accesses. But for B, let's say B is loaded into memory here, right? So first what we do is we access, so first we load this block B, or we load row K of B into memory, right? So let's call this row K. And initially it's K equals 0, right? And then, so we access this first element here, and that's going to be a miss because it's a cold miss. But then we don't actually go on to the next element here. These are the elements that are loaded into the cache currently, but we're not traversing it row-wise, we're traversing it column-wise. So that causes an issue for us because next we are accessing this element over here. And accessing this element, this element's not in the cache, so this is a miss. And then the next one's going to be a miss, and they'll all be misses all the way down. And then the value of K will change to K equals 1. And we'll have this block loaded in again. And this is again going to be a miss because by the time we get back here, this will probably have been evicted. And then again, as we go down, it'll be all misses. So the miss rate for B is actually a 1 because we miss everything that we try to access. And for C, the miss rate is a 0 because we're simply trying to access C at a specific row and column. And Yeah. So now what we could do is to make this better. So this isn't that great, right? So to make this better, what we can do is instead of doing the IJK pattern, we could try doing KIJ, right? And so what we're doing in this case is here we're traversing, so we access A in, for A we access a fixed value at I comma K. So the miss rate for that will be a 0, just like the miss rate for C here was a 0. And for B, we're also actually traversing it row wise this time, right? And it's because our K is going to be static, and the column is what's changing, and that's when it's a row wise. And same thing for C. The I is static, and the J is what's changing. So here, C is also being traversed to row wise, and so we already talked about the row wise traversal. So when the blocks are stored, there's going to be one miss initially, and then followed by 3 hits, one miss, 3 hits. So for B, it'll be 0.25 because we miss 1 out of 4 accesses, and for C, we also miss 1 out of 4 accesses. And so this is a huge improvement from our last, from the IJK pattern. And now we can also try this third pattern, which is JKI. And you'll see that this isn't an improvement from the KIJ pattern, because in this case, A is being traversed column-wise, and C is being traversed column-wise. So instead of our optimal conditions is both of them being traversed column-wise. Here we had 1 column, 1 row, but in this third case, we have both of them being column-wise. And again, similarly, when we access the item in the next row by going through it column-wise, the miss rates there will be 1 because we'll miss everything. So for A, the miss rate's 1, B, miss rate is 0, it's a fixed value, and C, the miss rate's a 1. So we didn't really go over, so we went over IJK, KIJ, and JKI, but they also have the counterparts because we have 3 letters, so we have 6 ways of arranging them if we permute them. And so, but these combinations, and these combinations all have the same kind of total miss rate. And so when we add together the miss rates here, so per iteration, this has a 1.25, this one has a 0.5, and this one has a 2.0. So we can see how it's possible for us to write cache-friendly code. And yeah, so this is one of the ways to do it. And I think you guys will be, you guys are asked to write cache blocking and cache oblivious code in PA5, and it's kind of a similar concept to this. And yeah, so if we actually plot, if you actually plot the cycles per inner loop iteration against the array size for these different nested for loop configurations, we get that so lower is better because less cycles means that it's faster. And we see that the KIJ and IKJ configuration that we calculated here actually runs the fastest. And so, and this is on a Core i7 processor where this was tested. And yeah, so that's how we can write cache-friendly code, and also how we can measure the performance of caches. And yeah, so basically, this is kind of a summary of how we can exploit our programs or write our programs to exploit these details. And So we can focus on the inner loops. That's where the bulk of the computations takes place. Work on maximizing spatial locality, work on maximizing temporal locality. And yeah, so this is how we can make our code run faster. And yeah, that's all I have for today. So if you guys don't have any questions, you're free to leave. And I will now stop this recording. And it'll be up tonight at some point, and I'll also post these slides tonight.